So hey nerds, this is Suman, and I found something very much strange when I substitute uncertainty as differentials. So over the 5 days, I have been learning about the quantum stuffs, and I got into the Heisenberg uncertainty principle, right? So this is the most fundamental foundations of quantum mechanics. That the more accurately you try to measure the position of a particle in space, the more your momentum is going to be spread out in that space. So in this video I'm going to show you what I have found, and this might be non-intuitive to everyone. I don't know whether it is intuitive or non-intuitive, but I would do my best to tell you. So let's get dive into the blackboard. So nerds, let's go dive into our the no uncertainty relation as differential. So our assumption is that our uncertainty uncertainty is differentials. So before starting this video, I would like to convince you that this might not be any new kind of theory or anything, or it might not be a reformulation of some new theory. It is just the might be the modification word, or the word modification might not be true for it. So it's just done by me as I was learning this stuff, right? So the basically uncertainty principle can be written as the position uncertainty and the momentum uncertainty is greater or equal h cut over 2. So the h cut is nothing but our reduced Planck's constant. So this is the uncertainty relation, right? So in order to tackle this fact and reformulate to get a new desired result, we have to move towards the de Broglie wavelength. So let's move towards de Broglie wavelength. De Broglie, let's say de Broglie equation, and it states that the momentum of a particle can be written as h over lambda. So the momentum can be written as h over 2 pi into 2 pi over lambda, and this is going to be momentum is h cut, means the reduced Planck's constant, and 2 pi upon lambda is nothing but the wave number. So this would be my equation number first, and this would be my equation number second. So now what I'm going to do is I'm using equation 2 in my equation 1, and I got delta x into h cut delta k is greater or equal h cut over 2. So the h cut and h cut will cancel out, and we got the position uncertainty and the wave number uncertainty is greater or equal to 1 over 2. And this is the quite remarkable result of quantum mechanics, right? So from this starting point, from this point, I'm going to substitute, I'm going to write something. This might not be intuitive to everyone. Whether it is true or not, I really don't know, but I had done it on based on my assumptions that I can write delta k is dk over d lambda into some delta lambda. So delta k is d over d lambda, and k is 2 pi upon lambda, and this is delta lambda. So if you differentiate this 1 over lambda, you get delta k is negative 2 pi over lambda square delta lambda. So the fact is that this quantity is positive, right? So the uncertainty are always positive, and we just have to take our uncertainty as positive sign, right? So the delta k can be written as 2 pi over lambda square and delta lambda. So in terms of our wave number uncertainty, we can write this fact. Whether it is true or not, I really don't know, and I do not have any professors to check this idea. So I am just posting this video in YouTube, right? So the uncertainty relation looks like 2 pi over lambda square delta lambda is greater or equal 1 over 2. So the fact is delta x into delta lambda can be written as lambda square upon 4 pi. So I have just substituted the value of delta k from here, and I got this relation. So from this fact, you can say that the uncertainty in position and wavelength increases as the wavelength squared. This might be one interesting point that we should have taken under our consideration. So this is the point. So up from here, what I am going to do is I am going to write delta x into delta lambda is greater or equal lambda square, and I am adding just p square in up and down. So there I got this term, right? This term. So the lambda and p, the product of lambda and p is h, and if it's squared, this is going to be h squared. So delta x into delta lambda is greater or equal h squared over 4 pi p squared. And from this you will again get one remarkable relation, that is delta x into delta lambda is proportional, inversely proportional to the momentum squared of the particle. And it is quite true, because if the wavelength increase wavelength uncertainty in position and wavelength depends on wavelength, it must have to immediately follow this relation, because the product of this can be written as momentum is inversely proportional to lambda, and see if one term goes on increasing, then another term will goes on decreasing. That's the inverse relation between these two things, right? And now what I'm going to do here is I'm just using the special relativity condition, that is from relativity. And more clearly I have to say it is special relativity, that is the energy can be written as m0 square c power 4 plus p squared, and that is c squared, right? So if and our assumption is that the particle is tending towards the speed of light, and this would be in relationship. If the momentum is 0, the energy is just going to be m0 c squared. So we are just using relativistic effects under this experiment. So while we are doing this experiment, we might consider the relativistic effect if we had accelerated the particles up to the speed of light nearly towards the speed of light, right? So our energy term can be written as gamma m0 c squared and it is m0 squared c to the 4 plus p squared c squared, and this is gamma squared minus 1. So if I take this here, I get m0 squared c power 4 equals p squared c squared. So in terms of our momentum squared, we can write gamma squared minus 1 m0 squared c squared. So this would be our relativistic effects under this condition. So this our relation, if we substitute this value, we get the relativistic effect under our experiment. So the position wavelength uncertainty is greater or equal h squared over 4 pi, and in terms of p square we have gamma squared minus 1 and m0 squared c squared. And if you know the fact that the particle has its associated some Compton wavelength, that is h over m0 c, and we have square in each term, so we have to use lambda square in there. So the uncertainty in position and wavelength is greater or equal lambda c squared over 4 pi gamma squared minus 1. The gamma is nothing but the Lorentz factor, and if you consider it as 1 over under root 1 minus v squared over c squared, right? And this would be our relation. So this would be our relation, and from this relation you can actually see the uncertainty increases as the Compton's wavelength of particle increases, and the uncertainty decreases, right? The uncertainty decreases to the factor r, sorry, it's not r, it's gamma squared minus 1. So if you try to plot a graph between these two facts, you get some inverse relationship, and it is also the fast decaying relationship, because it's not only gamma, it's gamma squared, so the slope is going to be very much steep as compared to gamma only. So this might be our another result. So this is our under the effect of relativity. So this thing we got, if we treat our uncertainty as differentials, and whether these things are true or not, I really don't know, because I do not have any professor to whom with I can share these things. Whether I am right or wrong, it doesn't matter to me. I had tried something that none other are trying. So I got this relation, that is delta x into delta lambda is greater or equal Compton's wavelength squared over 4 pi gamma squared minus 1. So you can ask me one thing that every physicist should ask, that Suman, what would happen if v is very much less as compared to the speed of light? So this is going to be our non-relativistic regime. So now the relativistic idea doesn't apply in our classical speeds, in the normal speeds, right? So we have to approximate this result. So in order to approximate, I'm going to do what? So I'm going to approximate gamma, right? So the gamma can be approximated like this. So gamma is nothing but our under root 1 minus v squared over c squared, right? And if you take square root over here, you will get gamma squared is 1 minus v squared over c squared raised to the negative 1. And now if we expand this relationship, you get gamma squared is 1 plus v squared over c squared plus v to the 4th upon c to the 4th plus so on and on. So and you can actually neglect the higher terms. So for our normal speed, we can neglect the higher terms and we get gamma squared approximately equal 1 plus v squared over c squared, and we get gamma squared minus 1 approximately equals v squared over c squared in our fact, right? So we get, so now if we have to substitute this relation, we get delta x into delta lambda is greater or equal lambda c squared over 4 pi, and in terms of gamma squared minus 1, this is the speed is very less as compared to the speed of light. We can substitute gamma squared minus 1 is v squared over c squared. So from this relation, delta x into delta lambda is going to be lambda c squared over 4 pi v squared, right? And now if you want to make it in terms of normal relativistic speed, you can actually write it as delta x into delta lambda is greater or equal. The lambda c is nothing but our h upon m naught c. So this is going to be h square upon m naught square. This is the rest mass of particle, and it is c squared into c squared over 4 pi v square. The c square term will cancel out and we get delta x into delta lambda. The position uncertainty, the product of position uncertainty and wavelength uncertainty is greater or equal h squared over 4 pi m naught square v square, right? So this would be the classical condition for this uncertainty, and this would be the relativistic condition for that uncertainty. So from here you can actually see that the uncertainty in position and wavelength, the uncertainty in, so you can actually ask me whether it is dimensionally correct or not, because the lambda c h upon m naught has a unit of meter, and there is a similar term here, m naught. In terms of c we got v, but they do both have same dimensions. So this is going to be our lambda square term, and this is going to be our meter into meter squared, and this is also the meter squared, which is dimensionally correct. If it is a dimensionally correct, why should I make the video? Right? So from here you can actually see, if we consider our relativistic effect, right? If we consider our non-relativistic effect, you can actually see that the uncertainty in position and wavelength is actually inversely proportional to the speed of particle. So the more speed the particle is going to have, the lesser uncertainty it is going to experience, or we were going to experience during the measurement. So if I plot the graph delta x into delta lambda, by keeping, whether I have to keep v or v square, it depends on my choice. So if I put v, it would be something like this, and if I put v square, the curve again goes on decaying faster, right? The curve will decay more faster because now it is going to decreases by v squared as compared to v. So the slope of this curve, so v squared is going to be larger as compared to the v. So this will decay as much as faster as compared to this. So if you put v as 0, you get uncertainty as infinity, which doesn't really matters, which doesn't really make any sense. So the uncertainty relation only works if v is greater than 0. Or we can actually say that if this relation actually holds true for any particle, we can automatically say that the particle might not be at rest, whether it makes sense to you or not. Or simply, in order to observe the uncertainties in quantum mechanics, the particle must have some quantity of speed that we are going to measure during the experiment. So now it's up to there. This was my whether I have to call it idea or not. So this is the thing that I had got. So if you want to look at it, you can actually look at it, and you can actually, if you didn't understand, try to rewatch it. So it might be as fast for me. I was talking might fast, and my English is not so good. So up to there. Bye bye, and do whatever do you want.